Take you through these first two problems to get you going on this worksheet. Okay, the first one says, what is the pH of a buffer containing 0.25 molar NH3 and 0.45 molar NH4Cl? Now, what's interesting here is that we have a weak base system. So we have NH3 concentration is 0.25. And our NH4 plus, which is the conjugate acid, is equal to 0.45. Okay, and I looked on the chart. The Kb for ammonia, which is a weak base, is 1.8 times 10 to the negative 5. So I'm going to use the base form of the Henderson-Hasselbalch equation. Okay, so I'm going to use this one. POH equals PKB plus the log of the conjugate acid over the base. So in this case, the log is going to be NH4 plus, which is our conjugate acid, over the concentration of the base, which is ammonia. Okay, PKB, I'm going to go ahead and do that now, is negative log of 1.8 times 10 to the negative 5. All right, so our PKB for this system, we're going to crank that out in our calculator, is 4.74. So there's where we're starting. Okay, and then we have this number and we have this number. So now we have everything we need to plug into the Henderson-Hasselbalch equation and to solve for the POH. All right, so POH is going to be equal to PKB, which is 4.74, plus the log of the NH4 concentration, 0.45, over the NH3 concentration, which is 0.25. Okay, so what I'm going to do there is just put that in my calculator and get an answer for POH. So my POH in this case is equal to 5. I got 5 right on the money. The answer sheet says something like, no, I didn't. I'm sorry. My POH was 5, right on the money. Well, that's not my answer. My answer is the pH. Okay, so we have one more step to go. My pH is going to be equal to 14 minus POH. Okay, so in this case, because I was using the weak base form of our Henderson-Hasselbalch equation, I get my POH, which I did get 5 for that. And so my pH is going to be equal to 14 minus 5, which gave me 9, right on the dot. The answer key is something like 8.99, 8.98. I'm not sure. It's just some difference in my rounding there. So there's my final answer, pH of 9. Okay, so the next one, we're building on this question, and it says, by how much will the pH change if we add 0.05 moles of HCl to 1 liter of the buffer in the previous problem? Well, there's a couple of things here that's making my life easy. 1 liter, yay! 1 liter means that I don't have to do a lot of crazy molarity questions. Now, the other thing we want to think about here is HCl is a strong acid. Okay, so the strong acid is going to react with the conjugate, the base portion of my buffer. Okay, so my buffer is made up of NH3 ion, ammonia, and NH4 plus. Okay, now this is the base, and this is the conjugate acid. Okay, so if I'm adding HCl, the HCl is going to react with the base. Okay, now this is very important. The NH3 is going to react in a one-way street reaction. Okay, I'm just going to write it as H plus because the Cl minus is a spectator ion. This is not an equilibrium system. This is a one-way reaction that produces NH4 plus. okay? And this is where we do what I like to call the BCA chart. B stands for before, C stands for change, and A is after. Okay, so before anything happens, we just fill in what we know. Since it's 1 liter of a solution, the molarity is equal to the number of moles, okay? So we have, at the beginning of the reaction, 0.25 moles of NH3. We're adding 0.050 moles of H+, and we start with 0.45 moles of NH4 plus. Okay, so that's what's in the system. Now, this is a one-way reaction. So the NH3 is going to react with the H+. And H+ is my limiting reactant. So it can only react, and it's all 1-to-1 moles. So it's going to go down by 0.050 moles and then stop. So everything is going to react in that quantity because it's a 1-to-1 mole ratio. So my NH3 is going to go down by that amount, and my NH4 is going to go up by that same amount. All right. So after the reaction's all done, we're going to get 0.20 moles is going to be left over. We're not going to have any of the H+ left over. That's my limiting reactant. Okay. And my conjugate acid concentration is going to go up to 0.5. Now, I'm emphasizing this again. This is a one-way street. This reaction goes to completion. This is not an equilibrium, okay? Because we're reacting a strong acid with a weak base, it just happens, okay? Now, what we can do is go back to our Henderson-Hasselbalch equation, where we know that we have POH. We already know our pKa, so I'm just going to leave it in there since it's the same system. Plus the log. Now, because this is all in 1 liter of solution, we can use moles instead of molarity because the moles divided by volume, they have the same volume. Okay, so my conjugate acid now is 0.5 and my conjugate base is 0.2. Okay, so now I can calculate the answer there for my POH. Okay, so my POH is going to be 4.74 plus 0.4, which gives me 5.1. But that's not my final answer because what I really want to know is the pH. pH is going to be equal to 14 minus POH. So we're going to do 14 minus 5.1, which gives me, I don't know why I got 8.86. I got 8.86. How did I get that? I had 14 minus, oh, I see. Here's where I went wrong. Where's my eraser? Doop, doop. 4.84. I had 4.96 right here. So much for my cheat sheet. Hold, just give me a second here. .5 divided by 0.2. Oh, gives me 2.5. All right, I'm just going to erase this and this and put the answer I got. Yes, I know. All right. I got 4.96 for my POH. So 14 minus 4.96 gives me 8.86. So the pH dropped by a difference of 9 minus 8.86. So it dropped by 0.14 units. Okay. I hope that helped. Give it a try. and see what you can do.